So let's try that. That's easier on my eyes. Okay. Okay. So the first chapter, we're going to talk about the Earth's atmosphere, kind of an emphasis on the Earth's atmosphere. But this course, we're talking, it's meteorology. So, of course, we're going to study the weather. And weather, by definition, is the state of the atmosphere at a given time. And when we mean state, we mean what is the atmosphere, what is the temperature of the atmosphere, what's the water vapor present, what's the precipitation doing at a given time. So weather is kind of immediate. Weather is like now, or weather could be yesterday or tomorrow. But climate is like 30 years. That's kind of what I'm going to distinguish weather from climate. So here's a weather map. It's colorful. All weather maps are a little bit different. Most weather maps, one of the things they do is they tell you the condition of the atmosphere basically about 5 feet, okay, from the Earth's surface. Okay, that's the conditions you see on a weather map. This particular weather map is color-coded and has numbers. The numbers and the coloring gives the temperatures, what we call the surface temperature is about 5 feet. Of course, the little snowflakes means it's snowing. You probably, how are you guys at, what's that right there? What's that line, blue line with triangles? It's a type of front.
Cold front.
It is a cold front, yep. That's a cold front, and what's this?
Warm front.
A warm front. How did you know that it was a warm front?
Suns or what have you. That's red.
It's red, and yep, it's red, and it has the shape is the little semicircles, perfect. And the cold front, okay, so this is cold. And so what this means, if this is a cold front, what that means is there's cold air coming in, kind of, the cold air in a cold front is coming on the side opposite of where the triangles are pointing. So you see the triangles are pointing there, so the cold air is on this side. So similarly, we have warm air up here. Cool. So this actually is just kind of a random day, late December. So weather can be very exciting, overly exciting. Everybody's adrenaline gets going when it snows, right? Everybody's adrenaline gets going when we have severe weather, thunderstorms potentially bringing tornadoes. So this is a graph from your textbook that goes back, each bar is a year, and the bar represents, the red bar represents damage in billions of dollars. And this is just for the United States. So United States, when did we get hit? Well, 2012, 2005, do you remember that was Hurricane Katrina? Yeah. And in that year, we had so many hurricanes that we had to go into the Greek alphabet because we ran out of, W's. So, yeah, it really varies with regard to, now, the red line is money, and the blue line is the number of events for that year. So sometimes, for instance, in 2012, we had a lot of severe events, but the money, to me, didn't quite correspond to that. It's interesting what gets hit. Back to the tornado. Of course, you guys are familiar with maybe already the scale of tornadoes. What's the most severe tornado? Do you know? F5. It is a F5. Very good. And those are very rare. EF4 is very strong still, obviously. So the whole weather versus climate, what I want you to kind of know is that weather is a short term. It could be now, it could be tomorrow, it could be yesterday. It could be like 10 days from now. What's the state of the atmosphere going to be? That would be weather. But what is it usually? The average, that's climate. And usually it's about 30 years worth of data for a general region, for a general time, like December, okay? So this is for, we're going to be looking at climatograms, especially in chapter 3. We'll be spending some time. But, you know, you get the word gram is kind of like a, kind of sounds like a graph sort of thing. And climate, okay, so basically you're graphing the climate. So the way you read climatograms is you see J for January, F for February, okay, exactly. You know, March, April. Okay, so here we have the June, July, and here we have December. So this is for New York, okay, and you can see for that month what was the record low, record high, average high, and average low. Okay? But this was taken with 30 years, and to me it should be the rolling average too. You know, if it's truly 30 years, then next year we basically throw away that last data point and take in the newest data point. Right. This is also, so that's a climatogram. This other one also deals with climate. And do you buy this? Basically, it's not temperature, but it's sunshine. Okay. Basically, each one of those numbers is the percent of possible sunshine. So, like, if we find Iowa, kind of find here, we're kind of a light green. Let's see, what do you think we are?
50.
Yeah, I'm liking that. You kind of follow that light green over. And that means in November, we run about, you know, there's about a 50% chance that we'll have sunshine. Oh, that's going out on a limb, right, in November. Okay, so climate data is really kind of, but it can be powerful. So clear in Unit 5, remember there's no Unit 5 exam, but we will touch a little bit on air pollution. So one of the things I want to talk about coming up next is how different elements of our kind of, how Earth is actually a system, because we actually have the firm Earth, we have the air over the Earth we call the atmosphere, we have the water element to our system, okay, and this is actually saying that actually we have little, if I could, in my own mind, I think of stick people, we have people on the Earth that are part of the system. And we definitely have our own interaction with the Earth, good, bad, and other ways. I stuck this one in there to kind of show you where meteorology falls. Okay, so meteorology, of course, is the study of the atmosphere. Kind of circled down here. There's meteorology. Meteorology falls under Earth and space science, which actually falls under natural science. Because I'll emphasize the word science in all of this, because we're going to talk just a little bit about the thing called scientific method, okay? The scientific method of discovery. And science, sometimes I think science anymore has almost a bad rap in kind of thinking it's something random. But it's not something random. Maybe that's my point. So you'll probably run into the scientific method or the scientific method of discovery before. And when I tried to kind of look on the internet and kind of concisely put this, there's kind of different flavors of the same ultimate thing out there. So first off, you can think of it in terms of you come up with some sort of question about the natural world. Now, I emphasize the word natural because the other side of natural is supernatural or spiritual. So when we talk science, already there is a, it's not a dotted line, it is a line, you know, between the natural world and the unnatural world. I'm not saying the unnatural world does not exist. I'm just saying there is a line there. So pose a question. And so it's kind of fun, you know, people are just generally curious. Little babies are curious, you know. So, and then based upon your question, you start to gather data or make observations. Or maybe you have observations and then you come up with a question. So it doesn't have to go in this order. Then at some point, you're going to come up with something called a hypothesis. And what a hypothesis is, sometimes they call it your best guess, but it should kind of be a kind of what's happening behind the scenes sort of thing. So your hypotheses, you're like, I see this happening with my own two eyes, and I think this is what's behind it, okay? And then based upon your hypothesis, you make predictions. Okay, so you're like, well, if this is what's going on behind the scenes, okay, then based upon my hypothesis, this other thing should be observed. Okay, maybe you'll even set up an experiment at that point. Okay, you can push your hypothesis, but the test for ultimately a theory or a hypothesis is can you predict anything from it? Halfway decently. Now, some would say that meteorologists don't predict the weather very well, but that's a whole other thing. So then based upon the results of your experimentation, you'll gather more data, make your observations of your experiment, and you might need to revisit your hypothesis and tweak it a little bit, or you might say, dang, I was right the first time. And at that point, you're like, okay, well, if that's the case, let's go do more experimentation, more observations. Okay, so you do that for a while. Okay. At some point, you become brave. And science, although it kind of definitely has a commonality of search for knowledge, science, it has its own little branches. So if you were in the area of atmospheric science, you would go ahead and get all the atmospheric scientists you knew and say, this is what I believe to be true. And go ahead and throw your hypothesis at them. These days, it's pretty easy. Well, I guess it's been easy for a while, but they have like literature, like journals. So you'd like publish in a journal. Back in Newton's day and stuff, you would publish on a tree, quite frankly. You'd like, so. So you share, you're brave enough, you share it with the scientific community, and I like to say that scientists are like little kids, that if there is anything wrong with your hypothesis, it will be found out. So that's okay. And there can be some modifications, but they like to shoot each other down. Now, if your hypothesis, maybe it needs to be tweaked again, you know, your colleagues throw pot shots at you, and or maybe it stands firm. At some point, the community will elevate your hypothesis to a theory if it stands the test of time and scrutiny. Okay, so a lot of people's pet peeves is that if somebody says, well, it's just a theory, well, you know, from what I've just described, a theory actually is quite is an extremely solid hypothesis, basically. So, I don't know why they say it's just a theory, but we do. So I got a couple of things off the internet, kind of basically what you see at the top there is you ask a question. Okay, observations, form a hypothesis, test the hypothesis. At some point, are you on track? If you're on track, then go ahead and report your results. If you're not on track, okay, go back and tweak your hypothesis. So this is just supposed to be kind of a funny little thing. Start out with a question, do research, hypothesis, experiment, study, facts, observations, analyze, conclusion, and then, you know, you emphasize this, you know, did it work or didn't it work? So, all right. So that was what I kind of wanted to say about the scientific method. So a little bit ago when we were looking at the current temperature and all of that stuff, wind speed, wind direction, couldn't find tendency, so you guys got me that if you don't find tendency on yours, don't worry about it, okay? I'll try to relay that to my other students. But this is where the stuff might have been coming from. Actually, if you drive, I don't know if you can see it from the road. See, Keokuk has a little airport there as you're going out of town, you know. They have something kind of like this. I don't know if you can see it from 61 or not. But each one of those gizmos basically does something. Like this one up here, I think, is wind speed and wind direction. And I'm not sure which each of these do, but they do something, and you can automatically see the stuff just sent automatically. So they're called ASOSs. The whole network is called an ASOS. So when we finally get to, I think it's in, maybe it's in Unit 4 or Unit 5, when we finally get to the weather forecasting part, we're going to see that this is really pretty good data that goes right to weather people. Actually, I should say what this data does is goes to weather people, and weather people put it in like computers, and then they use like models to see what the future will hold. That's kind of what they do basically. All right. So the Earth is a beautiful thing. The Earth is a delicate thing. And the Earth is kind of a system. I'm going to break it down on this slide into kind of 4 pieces. So whenever somebody says the geosphere, that's what they mean, the geosphere. And this says basically it's from the surface of the Earth down to the center of the Earth. There are no dinosaurs, but so it's about 4,000 miles to the center of the Earth. That's the geosphere. And then I have another slide talking about the atmosphere. But in general, what the atmosphere is, it's pretty thin, pretty, what we say, tenuous. The atmosphere is gases and some suspended solids and suspended liquids. But it's there due to gravity. And then the next sphere is the hydrosphere. Hydrosphere is all about water. I'm just going to briefly have a slide that shows the water cycle, the hydrological cycle. Of course, that's the water evaporates, it forms clouds, and it precipitates, and it does it all over again. Okay, and then the last sphere is biosphere. And that's what I'm going to talk about. So those kind of 4 things: the geosphere, the atmosphere, hydrosphere, which is water, and biosphere is life. And as far as we know it, our planet is unique, especially in that last criteria. So the atmosphere, this actually is taken, you see that little logo NASA there. So this is taken by, I think, a space shuttle, kind of taking this sort of glancing below. The dark color there is the Earth. And we're going to talk about layers of the Earth's atmosphere. So everything above this is the geosphere, and then the atmosphere begins. So that kind of orangish looking thing is the lowest layer of the Earth's atmosphere, called the troposphere. And then we have the stratosphere, which is here. This right here. I think it might be the whole thing. Stratosphere. Most clouds are in the troposphere. This right here, this is the troposphere. Most of the time. Okay, actually weather is there. There are a few special clouds, including clouds and weather. There are a few special clouds that are in the upper layers. And actually, I'm going to kind of take that back. I'm kind of thinking the mesosphere might be the next. It might not be the entire stratosphere there. That's just kind of a look at the Earth's atmosphere on edge. The hydrosphere, okay, or the water part. Maybe you guys already know this, but most of the water on Earth actually is tied up in the oceans. So 95%, or excuse me, almost 97% is in the oceans. Okay, the remaining water, 2.56 is non-saline. Okay, and of that non-saline water, it breaks down like this. Of the fresh water, almost 70% of the fresh water is tied up in glaciers. Okay, so then after that, it looks like we have groundwater. Okay, and then we have lakes and streams. So, and here is just, oh, I guess it's coming up. This is the the fourth sphere. This is biosphere. All sorts of green and living things. Okay, so again, Earth is unique. And then this is a photo from your textbook. We'll talk more about the water cycle later, but the hydrological cycle is the same thing as the water cycle. The whole evaporation, the evaporation of liquid water to form a vapor, then the vapor condenses to form liquid again. Anytime you see clouds, that's liquid water, and then of course it precipitates back down. Okay, so not only do humans then interact with the Earth system, but within those spheres there is different interaction. So this is a pretty picture showing you the water interacting with land. So that'd be the geosphere and the hydrosphere, and kind of the spray going up into the atmosphere. There might even be some biosphere there somewhere. This one, if you want to go ahead and put homework next to it, you can. I don't think you'll need the reference. I'll just put HW for homework. One of your homework questions is very similar to this. How are the 4 different spheres kind of interacting? Okay, mudslide. Can you see how would water, well, I'll just kind of answer my own question. Does it seem reasonable that water would be part of the mudslide? Yeah. And the mud is the geosphere. Do you see any biosphere being affected there? Yeah. The house is like very, yeeks. I guess biosphere are the trees, the 4 trees.
Trees, plants, animals,
Mm-hmm.
everything with that.
Yep. I'm not sure how much like notice they have for an event like that.
It's hard. I guess they had some around cliffs or what have you, but
Mm-hmm.
you don't know what's going to happen until it happens. Should be working on something. They already have something.
Yeah, I know. I had a friend who came from Japan, and she said that I guess they have some steep terrain in Japan, and it's illegal to like pull the shrubbery. Shrubbery? No, you can't pull the shrubbery because it like changes the dirt.
Well, Keokuk actually had an issue with that over on River Road. Some of the landowners pulled out trees, and the bluff got wet. The dirt
Oh,
went
man.
down. It covered up the railroad tracks. Railroad
No
got
way.
Real, it's one of the main bloodlines for the railroad, and they got real ticked off with that. So
Well, yeah.
people can't pull the trees out over the bluff anymore near River Road.
Huh. I guess they couldn't have known. I don't know.
Couldn't tell you. That's at least what I heard.
It's interesting. So Mount St. Helens, that is Mount St. Helens blowing its top. Okay. So of course, when a volcano goes off, can you see the whole geosphere, atmosphere, biosphere? It's not as obvious for the hydrosphere for me. I don't really see the water there. Actually, I guess I kind of do. I'll explain it in a minute. But so this is Mount St. Helens before and after. It like literally blew its top. Is that not amazing or what? And here's a figure from your textbook, and this is kind of why I put the title, The Earth's Healing Process, because this is many years after the explosion, and your textbook kind of describes how actually soil will go ahead and reestablish itself over the lava, and then on top of the soil you can get your vegetation growing, and of course then your animals can come back. So it does. So the reason that the water cycle is involved in a volcano going off like that is the ash it puts up actually can serve as particles that kind of seed cloud growth, basically. In order for clouds to form, they oftentimes need what they call cloud condensation nuclei, and the dust can do that. So, yep. Very cool. So the Earth's atmosphere is held in place by gravity. And so the Earth's atmosphere is not just gases. It's also, like we saw the volcanic ash, you know, that stuff you can visibly see, that cloud of dust, that's part of the atmosphere at that time. It's actually that particulates suspended like that we call aerosols. And of course, liquids suspended in. So the reason I titled this the Earth's current atmosphere, the gases in the Earth's atmosphere currently, is because I have a slide to kind of show you that when the Earth first formed about 4.6 billion years ago, the atmosphere was not mostly nitrogen. But right now, and sometimes I make this a test question, if I were to ask people on the street, what is the most abundant, or the gas that's most present in what they're breathing, they'd probably say oxygen, but it's not, it's nitrogen. Okay, so nitrogen, it's usually, you say about 80-20. And that doesn't leave percent for anything else. So the others are kind of like trace gases. But it wasn't always like that. So this is kind of how we got to kind of our 80-20 nitrogen-oxygen kind of gas mixture. So all of the planets, when they first formed, when our solar system first kind of became a solar system, and that was marked by basically the sun turning on. So the sun became a star, and then basically the planets that had been getting bigger and bigger, basically that was about as big as they were going to be. Okay, so that kind of froze everything. But all of the planets had, depending upon their size and what gravity could kind of make stick to the planet, they had basically the leftovers of what made our solar system, which is just hydrogen, helium, methane, carbon dioxide, and water. Notice no nitrogen. And actually, our atmosphere now, we don't have hydrogen. That would be flammable, right? So that actually, I don't know how long it stuck around, but hydrogen is very light. So it went away because of that. But the other thing is, I mentioned when our sun turned on about 4.6 billion years ago, it was all stars, including our sun, kind of go through this like crazy, just tantrum sort of phase. And they are extra powerful with regard to something called solar wind. And so the solar wind actually kind of swept everything downstream. So all the planets were kind of mostly bare of an atmosphere for a little while. So then we could start over. And when we first started over, what all the planets did was they were still kind of, this is really early in the formation of our solar system, and they started to crust over. So the Earth started to crust over. And then what happened was kind of like stuff that was trapped in the inside would kind of find a way out. Kind of volcanic sort of stuff, maybe through the plates that were forming. And so it burped. And what it burped, though, still wasn't nitrogen. Okay? So it released from kind of the inside of the planet. It started to give us an atmosphere, which was water vapor and carbon dioxide and sulfur. Actually, carbon dioxide, if you visit Venus, that it really has, that's what most of its atmosphere is. It's not nitrogen. So then after that, we still don't have nitrogen. Well, it had to cool down, okay? But I guess even before it necessarily cooled down, there was this time in our in all of the planets where actually there was all sorts of kind of random stuff floating around. Okay, comets from like way out by Pluto. Okay, and they brought us our water and most likely deposited nitrogen too. So it cooled down, it being the Earth. And when it finally cooled down, then that water vapor, that water gas that was in the atmosphere could go ahead and begin coming together and forming clouds and raining. Can you imagine what it would be like to be like here with the first rainfall? That'd be a rush. So anyway, it kept cooling down, more and more rain, okay, and it created our water cycle. So the water could go ahead and kind of make large areas of water. And some of you guys may know, and we'll talk about this later, our planet used to basically have all of the land used to be kind of squished together, and then the whole other part was water, okay? So in that large, those large bodies, or that large body of water, we could have life evolve. And it took a long time, I don't know how much, but it took a long time for life to evolve, and it's first evolved in plant life. And so the little plants that actually were smart enough to do photosynthesis, not they're really smart to do photosynthesis, but I think they're pretty smart to do photosynthesis. Actually, they took in the carbon dioxide and they spit back oxygen. But the first oxygen that came out from the plants, from photosynthesis, one of the things about oxygen, and yes, my background's in chemistry, so I teach chemistry. So there's a periodic table in here for a reason. So on the periodic table, the O is for oxygen. One of the things about oxygen is it's very reactive. And so that first oxygen that plants gave up in the atmosphere, it actually reacted with anything it could. And what worked well was actually in the Earth's crust. Okay, basically the elements in Earth's crust and oxygen, they go together just like that. If you're a rock person, you know that a lot of the cool rocks actually are like oxalates or something like that. Okay, so then after finally all of the like reactive elements on the surface of the Earth reacted with oxygen, then finally oxygen can start building up to the 20% we have today. Whew, are you cold? So this says BYA, by the way, and what's BYA? Not bring your own, okay. Billion years ago, that's right. So 1.5 billion years ago, we finally, the oxygen kind of started, or pretty much stabilized. There you go. That's the story of the 80-20 nitrogen-oxygen. So with regard to gases, it's kind of helpful to look at gases and break them up into permanent gases and variable gases. So when we say a permanent gas, it's permanent mostly in its composition. Okay? So there are three main permanent gases. Nitrogen, about 80%. That last column is going to come in handy later in the class. Okay, so nitrogen we said is about 80%. Okay, so the deal with nitrogen, of course, you guys would probably tell me that in chemistry, if you're going to talk about nitrogen, use a capital N for nitrogen. The other thing about nitrogen is it's one of 7 elements that actually, I say, doesn't like to be alone. So if you find one nitrogen atom here on Earth, that's a chemical bond. You're actually going to find a second nitrogen atom. They're diatomic. It's a diatomic element. So the deal is, if you were to weigh that molecule would weigh that much. Okay, and actually, if you kind of dabbled in weighing molecules, the units over here would be AMUs, or atomic mass units. So how much does an N2 molecule weigh? 28.01 AMUs. Okay, so there's 3, so that's nitrogen. Oxygen's about the 20%. Okay, so oxygen is kind of like nitrogen in that you see the little subscript 2. That means actually oxygen's like that too. It doesn't like to be alone. You'll always see 2 oxygens connected running around. And it weighs, this last column, okay, it weighs 32.00 AMUs. The third one is not even a percent, and it's argon. Argon's awesome. It's like on the periodic table, if you've kind of played around with elements, you know that there's that last column of elements. It is so awesome. They have 3 names. That last column is called rare gases, inert gases, and noble gases. It's all the same thing. So argon is the pirate's favorite element. And then we kind of have some trace things. Neon, helium, krypton, xenon. Actually, those other ones underneath it, those are all rare gases too. So these guys are all rare gases. Okay. And notice how much hydrogen we have in the atmosphere. Not very much. Remember this third column is the percent, so 0.00005%. But xenon, oh my gosh, look how much it weighs. 131.3. That's very heavy. So actually this number, 131.3, you go over to the periodic table and you find XE, it should say 131.29. Okay, so that was permanent gases, and this is variable gases. There's 3 variable gases that I want to talk about. They're variable because their composition varies, and they're variable because depending upon where you are on the planet, their composition will vary. Now remember, these are gases in the atmosphere. Okay, so when you see them, you're like, oh yeah, I get it. So like, doesn't the water vapor vary? Okay, so that's water vapor. I think I've seen 1 to 4%. I think it says 0.25 by volume. That might be by something else, but I've seen it listed. It varies from 1 to 4%. And how much does an H2O molecule weigh? And of course, that's over there. All right. So it varies from hour to hour sometimes. Carbon dioxide, the symbol for carbon, or the formula for carbon dioxide is CO2. It is definitely a variable gas. We'll kind of look at why it's a variable gas. 0.038% corresponds to, you're going to see it on a graph here in a minute, this percent is 380 parts per million. Okay. Which, so carbon dioxide is, I want to say that dirty gas. I mean, it's actually a pollutant, carbon dioxide. Okay, and the last one, variable gas, is ozone. So ozone is made up of oxygen. So if you go here to the second column, you see an O with a little subscript 3. So that means there are 3 oxygen atoms stuck together to make one ozone molecule. Okay, and again, it's a variable gas, so that means it's going to vary. Its percent is going to vary by location and time of year, time of day. Okay. So we'll talk about each of those variable gases. Starting with carbon dioxide. So that previous slide said 0.038, and I can't remember when, but it was a kind of a big hairy deal. It's now about 400 parts per million, so 0.040. It has, and I'll show you a graph here, how it's gone up year after year after year. Carbon dioxide can become part of our atmosphere because of natural reasons. For instance, when we exhale, that's animal respiration. We are animals. We exhale, that's respiration. We spit out carbon dioxide. When plants or animals decay, part of the decay process is the gas, carbon dioxide. When volcanoes basically burp the internal gases of the earth, they give more carbon dioxide to the atmosphere. Okay. There are also man-made sources of carbon dioxide being added to our atmosphere. And if it's a man-made source, we call it anthropogenic. So, like if you're an anthropologist, you study people. So anthro means people, genic means comes from. Okay, so anthropogenic comes from people. So of course the biggest source of putting carbon dioxide in the Earth's atmosphere is burning fossil fuels. And fossil fuels would be oil, gas, and coal. Well, we can actually remove carbon dioxide from the atmosphere. And in most cases, I'd say all these cases, where does it go? Well, it kind of becomes, it's broken down and or it becomes part of the geosphere. So one way is when plants suck it in and spit back oxygen. And the other is if you make soda water. Because like what's soda water? Basically, it's water that you have put carbon dioxide into. So our oceans are great at basically being a big old reservoir where depending, and this is like a Henry's Law thing, but depending upon the concentration of carbon dioxide over there, some of it will be forced into that. But that's a little bit temperature dependent too. So if you start monkeying with the temperatures of the oceans, then you change kind of the solubility or the amount of carbon dioxide gas that's going to dissolve. So this is the carbon cycle, carbon dioxide or carbon cycle. Basically, wherever you see a red line, that is carbon dioxide going into the atmosphere. Okay, and wherever you see a blue line, that's carbon dioxide coming out of the atmosphere. So how are we doing? Looking for a good stop of place. Okay, next two slides. All right. So I'm going to show you a graph here in a minute. And you're going to see two trends in this graph. One trend in this graph is going to be a yearly trend. Basically, each year carbon dioxide goes up and then it comes down. And this is why. It's like a seasonal swing. And it has to do with plants. So if we didn't have plants, we wouldn't see that little up and down over the course of a year. We know that plants are great in taking in carbon dioxide, right? So here's the deal, though. It's a delay. So you think like springtime is when the most plants are, but springtime is when the plants are getting started. So think of it that way. So it's not until kind of like fall that we see the benefits of the plants doing their thing. So in fall time, you kind of see a kind of a downward swing to your carbon dioxide. In the springtime, it's kind of actually, you see a lot of carbon dioxide. Okay. All right. The other trend you're going to see you're going to see both trends. You can kind of see this little wiggle. Okay, that's a yearly wiggle. And then you're going to see this ongoing trend from year to year. And that's the famous increase in carbon dioxide in the atmosphere. Now, why are you going to see that trend increasing in carbon dioxide? Well, it's what I said a minute ago about us burning fossil fuels. And when we get gas at the gas station and burn it in our car uses it for fuel, and out the exhaust comes water vapor and CO2. It just does. But the other thing, not just burning fossil fuels, but what man has done, what we have done, continue to do, is to remove large amounts of trees. So the whole deforestation is probably kind of obvious because the trees are great at removing carbon dioxide. So basically you're removing what we call a carbon dioxide sink. So here was the diagram I was talking about. So can you kind of see the little, can you kind of see the little jags? Each little jag is a year. So this goes back from 1960 to, current data-ish. Okay. So let's see. So each jag is because of the season, but the overall trend is, like I said, because burning fossil fuels and deforestation. So let's see if this thing works for us. The latest data. So it's kind of historic. You see from the title of the slide that this data was taken on an island, a Hawaiian island. Okay, so it started years ago. It's a great monitoring station. It was in the news maybe a year or year and a half ago about needing funding. So I hope they found their funding. And when I pull up latest data, it's actually going to be like what it was today. And I didn't look at it today. Maybe. Yay. See, it's loading twice. Oh, direct. Now, if you're like my kids, you'd be like, Mrs. Snipes, you have way too much stuff open. That's your problem, Mrs. Snipes. You're probably right. Okay, so two things with carbon dioxide, we looked at the 0.038 or the 380 parts per million, and then it said 400 parts per million. Well, right now it's 405 basically parts per million. It's going up. So this looks pretty flat. Like what's this is okay, and I know it's maybe this. You might think this is anomalous, but to me it's got a little bit of hourly data there. I think that's what that is. But if you, I'm going to pull up one more curve and kind of put this in perspective. This is just for one day. Yeah, I remember when it hit 400 because I read an article. Oh, that's kind of cool. This one, okay, so this one is different, isn't it, guys? Notice that this starts back in the year 1750. I'm not good with history. I wish I was better, but you figure Industrial Revolution, mid-1800s maybe, okay? So Industrial Revolution, we start burning fossil fuels, and I think that's kind of, and you might be like, well, Mrs. Snipes, who was measuring carbon dioxide back then? And we can get into that later, okay? But yes, we do know carbon dioxide levels, and then, of course, you can kind of see the acceleration there. Probably where you start to see this right here, these bumps, this is where the data came from the Hawaiian island, and this was another source of the carbon dioxide data. But if you've heard people talk about the hockey stick sort of carbon dioxide, this is what's supposed to look like the bottom part of the hockey stick and kind of the business end of the hockey stick. Okay? So that's all kind of a little depressing, but it's okay. Let's go ahead and take a break, another 10-minute break, and come back like about 7:35-ish or so for, guess what, it'll be Friday then, kind of. Segment C. I'm hoping to get through chapter 1.